Good afternoon. Myself Sandhya Harikumar. Together with my co-author Surya PV, we are pleased to present our paper K-Medoid Clustering for Heterogeneous Datasets. Our paper ID is 45. So this is the outline of my presentation. First is introduction, K-Medoid clustering, then the related work, proposed distance measure, the probabilistic approach for similarity measure, the proposed phases of K-Medoid clustering, and finally the experimentation. To start with, all of you are aware of clustering, one of the main data analytics platform wherein it seeks to identify homogeneous groups of objects such that the within cluster distance is increased and intra-cluster distance is decreased. So datasets with heterogeneous data types, however, now are common in real life, such as educational domains, finance domains, healthcare, sales and purchases. However, traditional clustering algorithms tend to deal with clustering of only homogeneous data types, but conversion of heterogeneous data into homogeneous data leads to loss of information. So, clustering such heterogeneous datasets is really a challenge. So, the objective of our paper is to come up with a new K-Medoid type of clustering by leveraging our new proposed distance measure, which is based on vector, for datasets with heterogeneous attribute types. So the issues to be dealt here with are how to compare the two heterogeneous data objects for similarity. The other thing is about the structured format which is necessary to be given to the data, but all the data types cannot be converted into homogeneous data types. Another thing is the main K-Medoid clustering for enabling clustering of mixed as well as pure numerical, categorical and binary datasets. So this is just to give you a description of the problem. Let us consider an instance of bank dataset which I have got from UCI repository consisting of various mix of attribute types. So let us consider the numeric attribute here, which is duration. In this, the disparate characteristics is followed by different types of attributes because numeric follows different, categorical follows different and binary follows different. For example, numeric attributes always have a natural ordering because 261, for example, is always greater than 151. This type of ordering is always followed. However, in categorical attributes, there is a discrete probability distribution. We can never have an ordering like management is greater than technician or technician is greater than management. The other thing is about the binary attributes wherein we can just check for the equality of the attribute values. So we can say that it is following Bernoulli distribution. So thus it is displaying or it is exhibiting disparate characteristics. So the major contributions, the goal of our paper is to come up with a modified version of K-Medoid clustering such that it is seeking to find the most potential medoids which can form good representatives for clusters. But for this, we are trying to adopt a probability-based similarity measure for categorical pairs together with L1 norm measure for numerical as well as Hamming distance for binary attributes. So clusters with mixed as well as pure numeric, categorical and binary datasets is to be possible. That is the main goal of our paper. So let me start with the basic version of K-Medoid clustering. As you all may be aware of that any K-Medoid clustering will start with an initialization phase wherein it is going to randomly select k of the n data points which we term as medoids. Then what we do is, as per the Euclidean norm, we associate each data point to the closest medoid. When the cost of the configuration decreases, we go on repeating the two steps such as that for each medoid, for each non-medoid data point, we swap MNO and again compute the cost. The cost here is nothing but intra-cluster distance. If the total cost of the configuration is increased in the previous step, we undo the swapping. This is the traditional partition around medoid algorithm. So here you can see that medoid is always a point in the data set. So we have referred to various papers, however these three are our main reference papers. One is a K-mean clustering algorithm for mixed numeric and categorical data by Ahmed. Here they are providing a distance measure for clustering mixed datasets. They are making use of modified Hong's cost function. Another thing is projected clustering for categorical datasets wherein they have come up with a new distance measure, but their intention was the predicted clustering, that is subspace clustering. Similarly, there is another algorithm which is for predicted clustering. However, there is a typical phase of finding the Medoids, so we have chosen that phase in our proposed clustering analysis. So let me start with the distance measure for heterogeneous data sets. So as I told you before that our aim is to come up with a distance measure for heterogeneous data sets so that we can cluster well. So what we are doing is we are integrating various types of distance measures of categorical, numeric as well as binary data sets. So here the main concern is for categorical pair of values we are following a co-occurrence based approach. For numerical pair of values we are following L1 norm, that is Manhattan distance, and for binary pair of values we are following Hamming distance. So how to integrate these three measures, that is our contribution. So the solution approach is saying that the proposed cost function, which is to be minimized for clustering mixed data sets, has mainly three components as specified before. What we do is we try to amalgamate or integrate all these measures which we call as Vri, Rj, that is the distance, and how do we integrate this will be explained in the subsequent slides. To start with, let us consider the distance measure for numeric attributes. This is an example, simple example where only the numeric attributes are there. If I want to compute the distance between the data ID 0 and 1, what I do is I just take the Manhattan distance between the two values. So here you can see that it is just 2261 minus 151 plus 2143 minus 29. That means this is the combination of Manhattan distance for each numerical attribute. So what we have understood is distance between two numerical attributes for the data points 0 and 1, we have come across 2224. However, this data set also consists of categorical attributes. Now let us focus on the categorical attributes. So in a nutshell, what we are doing is we are dealing with each type of attribute in a separate manner. So this is the second type of attribute which is present in the bank data set as I showed before. So here there are three categorical attributes, that's job, marital, education. What we do here is we try to seek the probability of one particular attribute with respect to other attribute. So here again, when I want to compute the distance between two attributes with respect to the job attribute, two rows with respect to the job attribute, what I do is I compute the probability of married given management. If you have a closer look, again in job there is a particular value management. What I do is, what is the probability that married will occur given management data. So when it comes, we can again have a look that there are two values or two rows wherein management value is present, and again within those two rows only a single row is there with married value. So that means 1 by 2 is the probability, that is probability that married occurs given management. This is known as co-occurrence. Similarly, I can just give you one more. For example, probability secondary given technician. So if I look into the technician, there is only a single row which is having technician value. Now within that technician value, there is only a single row for education which is secondary. So that means I can say it is 1 by 1, that is 1. That means within a given row having technician, the probability that secondary value will occur for education is 1. So subsequently we can find all the other values. So this is what we do for categorical attributes. After finding these probabilities, what we do is, in order to find the distance between the two, we are doing the summation of probability of I with respect to given x, probability of I not w with given y minus 1. So here x is the subset of values for aj that maximize the quantity of this probability piw given x plus pi not w given x. So this is what actually the distance between the pair of values x and y which are actually with respect to ai. So here there is a compulsion that if I am talking about the distance between two rows with respect to a particular attribute, I am also considering other attribute, because without that I cannot measure the probability. Now for binary attributes, so in the given data set there were also few attributes which consisted of binary values. So something like housing, loan, default, Y and all. So here what we do is, if I want to compute the distance between two rows, I don't have any other thing but just to find the Hamming distance between the two. So if I look into the housing and loan, I just say, okay, what is the difference, or what is the distance, or what is the similarity between row 0 and row 1. What I take here is, yes, it indicates same, no indicates same, no again indicates same for default, and no indicates same for the Y attribute. That indicates there is no difference at all, and both row number 0 and row number 1 are same in terms of binary attributes. And that is the reason we are getting the value 0. So as you all are aware, similarity 0, that means it is high, similarity 0 means it is less similar, and similarity high means it is 1 means it is more similar. So what we do is, we are combining all the three measures and we give it in the form of a vector. So that is what is I mentioned before about the vector based distance measure. So vector representation of the distance measure for the entire data set consisting of various types of attributes we give as L1 norm, probabilistic approach, Hamming distance. So in this example which I showed you, it turns out to be that L1 norm 0.14, 3/2 and 0. This is an example. So with this proposed distance measure, we are now going to find the clustering of a given data set which consists of mixed, numeric, categorical as well as binary data set. So we are also proposing new phases for K-Medoid clustering, as I already gave you the basic version of K-Medoid clustering. However, we are having three phases in this. The first phase being initialization phase, the second phase being iterative phase, and the third phase being outlier detection. So the initialized phase is actually to find the potential set of Medoids, and this is following a greedy approach. What we do here is, let us consider that we have many data points, say n, and randomly we will choose a sample of those data points which I call it as a dot k. It is just a size where a is a large number, and based on this random data set we compute again, or we find again k Medoids. But instead of finding k Medoids, if we are intending to form k clusters, we are actually finding b dot k, where b is a small number. And this b dot k is the final set of Medoids which we are getting from the first initialization phase, and this b dot k set Medoids are forming the potential set of Medoids for further phases of K-Medoid clustering. Now let me focus on the iterative phase, because this is the phase wherein the points are really assigned to the clusters. So as I told you before, that Medoids are actually the representative of the clusters. So here there is a diagram which is showing what we do here is, for A, B and C are the Medoids. What we do is, we find the distance between A and B and A and C. We find which is the shortest distance, which I call it as delta, and all the points which are within this delta distance, we assign those points to the Medoid A. Similarly, if C and B and C and A are there, we again find which is the shortest distance of C from the remaining Medoids, and we find all the points which are closest with respect to delta. So assign points to a particular Medoid is based on the unified distance measure. This distance measure, till now in traditional algorithms, what we do is either we use Manhattan distance or Euclidean distance, that type of things for numerical attributes. However, we are defining a unified distance measure as I showed you before. So based on that unified distance measure, we are actually finding the distance between the Medoid and the remaining data points, which are actually heterogeneous. So we are calculating the unified distance delta I of each Medoid to its nearest Medoid. And then what we do is, we find all the records which are forming the subset of the original data R within the distance delta I. So this is what is one of the main phases in how to assign the points to each Medoid. Next, what we do is, we are evaluating the clusters formed. As I showed before, assign points is actually assigning the points to each Medoid. Now the third one is, in the iterative phase itself we have something known as cluster evaluation. That means we are evaluating the cluster and seeing whether the formed clusters are good or bad. And for that we are using the measure which we call as Davis built-in index, which is a very well established measure for evaluation. And this measure is given by 1 upon k, where k is denoting the number of clusters, and for each cluster we are trying to maximize Dij. So what is this Dij? It is actually the ratio between the within cluster and intra-cluster. So within to between cluster distance ratio for ith and jth cluster is actually given by Di bar plus Dj bar divided by Dij. So what is Di bar? That is the average distance of each point within a cluster to its medoid. What is Dj? The average distance of each point within a cluster Cj to the medoid Mj. And Dij is the distance between Mi and Mj. That is Dij represents the within cluster or inter-cluster distance. So maximum value, so you can look into the equation and you understand that maximum value of Dij actually represents the worst case scenario within to between cluster ratio. The optimal clustering solution will always have smallest because of the measure Q. Now this is our experimentation part. Due to lack of time, what we have done is, though in the paper we have given many more experiment results, but here we are only showing for Australian dataset and zoo dataset. Australian credit card dataset is actually heterogeneous dataset consisting of various types of attributes, and we find that we clustered it for 2 clusters, and we found that the purity, the index value for cluster number 1 and cluster number 2 together, we are getting purity is equal to 0.882. What this indicates is the positive and negative classes. In cluster number 1 there were 288, and in cluster number 1 there were 62 negative classes, and in cluster number 2 we found that 19 positive as well as 321 negative data instances were present. This indicates that the purity of this particular cluster formation is equal to 0.882. So purity is already a well established evaluation measure, which is mainly for the type of cluster which we see, provided we have the labels. So Australian credit card dataset already is a labeled dataset, so we can find the purity value for this. But the result which I showed was from the paper K-means algorithm. So when we tried the same Australian credit dataset with a proposed algorithm, we found that we are getting better result. If you have a look, you can understand that purity is going up to 0.9, which indicates that this is a better clustering as compared to 0.882. So definitely purity value is better in our proposed clustering method. Similarly, DBI, that is Davis built-in index, which I explained before, 0.38, which is a lower value. It can have a value between 0 and 1, but 0.38 is a lower value. Definitely, as I explained before, lower value indicates better clustering. So this is definitely a better clustering as compared to a related work clustering, which is K-means. Again, this is another data set which is zoo, but this data set was actually a binary data set. So here also we tried for 2 clusters. In this we found that in cluster number 1 there were 33 instances belonging to one class and 8 instances belonging to other class, which I call it as false. The cluster number 2 had 8 instances belonging to one class and 52 instances belonging to other class. On finding the purity value, we found that it is 0.841. We applied the same data set for our proposed algorithm also for clustering of 2 data sets. What we found is we found a very good result, because when we looked into the first cluster we found all the data instances belonging to one class as it is, and for the second cluster we could find the data instances belonging as in the second class. Because of that the purity has come up to 1, because as per the labeling of the data we could get the correct answer. However, actually the cluster compactness is not very good, but depending on the label we could find that this clustering method is good compared to K-means algorithm. So this is about our performance analysis. I am not able to show more because of the time restriction. So that's it, and these were, I will also show one more, because these were the different data sets like zoo or Australian credit card, which I already showed, but we also compared with vote data set, bank mixer, as well as bank numeric. So these two things are showing us the purity as well as the dBi comparison. So we can find that purity is always higher in our case, and dBi is also, though not very low, but it is in the lower phase. And when we are comparing k-means with our proposed, we find that we are always getting purity value in proposed k-medoid higher than all the remaining k-means. So we can claim that our proposed measure or our proposed clustering algorithm together with proposed distance measure is a better one. So I am not able to show further things. So that's it about my presentation. These were the references. I had referred many, but I showed you in the related work 3 main literature survey, but I have also looked into various other references. Okay, thank you.